This video explains what the fundamental theorem of calculus exactly says and how to use it. If the graph of a function little f is always above the x-axis, the fundamental theorem of calculus gives a way of calculating the area which is below the graph y equal to f of x above the x-axis and between the vertical line x equal a and x equal b. And in that case, this is how we denote the area under the graph of f of x, that's your f, between a and b, where a is smaller than b. So that's a new notation for your area, and this is the way to find it. This area is going to be obtained by finding an antiderivative. So let's say the antiderivative is called capital F. You sub in the value of b, the value of a, and you subtract. Sometimes as an intermediate step, it's convenient to say, well, I found an antiderivative, it's capital F of x. I just keep track of the endpoints a and b, and at the next step, I will sub in, right? So you will see this notation, which is usually an intermediate step, which says, okay, I found an antiderivative, and I'll substitute next. So if your f is positive, this is exactly the area under the curve. Now you may have noticed that here it says the signed area, so that's the new part. So let's now look at the example of a function whose graph wouldn't always be above the x-axis. Signed area means we're going to have a sign, positive or negative. What happens is if an area is above the x-axis like this one, it's counted positively. And if it's below the x-axis, it's counted negatively. So for example, let's say that this area is 3 square unit and this one is 1. When you calculate the integral of f of x dx between a and b, what you would get is 3 minus 1. The reason for the sign being an area above the x-axis is counted positively and one below the x-axis is counted negatively. The theorem says you need to find an antiderivative of little f of x, and any one will work, so you don't really need to have the plus c. Usually, since you can pick the one you want, you pick the one where the constant is 0. So let's say you want to calculate the integral between 2 and 3 of 2x dx. The method says find an antiderivative, that would be x squared. Let's say x squared plus 7, any antiderivative between 2 and 3. When you sub in, you're going to get 3 squared plus 7, that's f of b, minus 2 squared plus 7, that's f of a. So you get 3 squared minus 2 squared plus 7 minus 7, and the 7's disappear. And if you had put a 9 instead of a 7 or a square root of 2 or whatever you wanted, they would have disappeared in the calculation also. This is why you don't need any c. This integral, when you have endpoints, is called a definite integral. And that's because you get an actual value, you get a number. Remember in the past we had this same symbol but with nothing here, and that was denoting the set of all antiderivatives of the function little f, and this wasn't really well defined because of the plus c, which is why it was called the indefinite integral. Let's now look at a few properties of the definite integral. After that, we will have everything we need to know and we will be looking at example. If you're taking notes on what we're doing here, everything you need to know is on this slide. So let me illustrate the first property by a drawing. The property says that if I add the area between A and C, which is this one, to the area between C and B, which is that one, I will get the area between A and B. Yes, we totally believe that. Okay, it turns out that it's easy to see on a drawing if f is positive and a is less than c and c is less than b. It turns out that it also works no matter what the sign of f is and no matter what the order of a, b and c is. Let's now turn to the second property. It says that swapping the endpoint a and b just changes the sign. And we can believe that because if capital F is an antiderivative, the formula said sub in the value at the top, subtract what you get when you sub in the value at the bottom. But in that case, if A is at the top, we would get capital F of A minus capital F of B, and we indeed see it's the same. This formula can be useful because if for some reason you don't like the order of the endpoint, say because you like to have the small one at the bottom and the large one at the top, what you can do is swap them, provided you add a negative sign at the front. Let's look at the third one. It says that if you want to integrate the sum of two functions, you can actually integrate them separately. And that's consistent with this formula here, because in that case, let's say you would get capital F of B minus capital F of A, and this would be capital G of B minus capital G of A, and you would be getting the same thing here. Let's now look at examples. Let's do the first one. The method says find an antiderivative for the function inside, so for x squared, and that would be x cubed on 3. That's one possible antiderivative. And as we said, we keep track of the endpoints 0 and 1. Then the methods say take the number at the top and sub in the function. So we get 1 cube on 3. We now do the same thing with the number at the bottom. We sub in and we subtract. So minus what we get when we sub in the number at the bottom. And we get 1/3. If you remember, this is exactly what we got when we used the Riemann sum. Isn't this so much easier? If you're fine with this first example, maybe you want to pause the video and do the others by yourself. Okay, so step 1, let's find an antiderivative, x cubed on 3 again, between 2 and 5. And now we sub in 5. We subtract what we get when we sub in 2. So that's 125 minus 8 on 3. So that's 117 on 3. We notice that when we add the digits we get 9, so that's divisible by 3. Let's see how we can break this into two multiples of 3. Of course, you can also pick your calculator. I'm sure mine is somewhere. So we get 39. Another good time to pause the video if you'd like. This one, antiderivative is x cubed on 3. The endpoints are 1 and -1. And we get 1 cubed on 3 minus -1 cubed on 3, which really is 1/3 plus 1/3. And so, these two terms are equal. Actually, if we draw what's going on, it's going to be very clear why that's the case. That's the graph of y equal to x squared, and we're integrating between -1 and 1. So really, we are trying to find this green area. We proved in the first question that this area was 1/3. Because of the axis of symmetry here, these two areas will be equal. So this one will be 1/3 too. When you integrate blindly without looking at the graph, you won't see that. So in that case, if you do this drawing first, you don't need to do all of this at all. You could have said that twice the area between 0 and 1 of x squared dx, which was found in question A, so that's 2 times 1/3, and that's 2/3. Question C was a preparation for question D. If we start from an even function, the vertical axis will be an axis of symmetry. So the integral between 0 and a and the integral between -a and 0 will be the same. So what we will get is twice the integral between 0 and a. If you'd like, this is the general case, and that was a particular case when the function is x squared. So I'm going to box this because we can consider this as a theorem. That's a property we just proved. Let's do more. If the function is x cubed, one possible antiderivative is x to the 4th on 4 between 0 and 2. If I sub in 2, If I sub in 2, I get 2 to the 4th on 4. And if I sub in 0, I get 0. So that's 16 on 4, which is 4. Now let's do the same for this one. It's the same antiderivative. When I sub in, I get 2 to the 4th on 4 minus negative 2 to the 4th on 4, which is 4 minus 4, and that's 0. So suddenly we wonder why we get 0. Maybe by sketching the graph we could have seen from the beginning we were going to get 0. And indeed that's the case. If you draw the graph y is equal to x cubed, and if you integrate between negative 2 and 2, you will get these two areas, this one here and that one there, because remember that the integral calculates the area between the curve and the graph. So we said that this one was equal to 4, this one there. And this area is also equal to 4, but remember, this integral is not the area, it's the signed area, meaning it's going to count positively an area which is above the x-axis, and it's going to count negatively an area which is below. That means that the integral will be plus 4 minus 4, and it will be 0. Again, because we integrated blindly without looking at the picture, we had to do some calculation. But the symmetry in the graph would have been enough to get the result. Like on the previous slide, this is a special case to give us the idea of what happens in the general case. Well, if the function is odd, its graph is symmetric with respect to the origin. Remember, that means you can rotate the part of the graph 180 degrees and it will come exactly on the other one. When you do this, whatever was above the x-axis will come below, and whatever is below will come above. That means every area will be counted positively and negatively, and everything will cancel. This area will be 0. So when you integrate an odd function on a domain which is symmetric with respect to the origin, so these two numbers are opposite, you will always get 0. And that's because the graph of an odd function is symmetric about the origin. Let's look at something else. It's x cubed again. We use an antiderivative of x to the 4th on 4, again between 2 and 2. And we get 2 to the 4th on 4 minus 2 to the 4th on 4. Again, that's 0. And again, we wonder why. Well, what happens in this case? These two endpoints are the same. So you're trying to find an area, but look what the area will be. If that's your curve and that's 2, you're really looking at the area of this line segment. The area of a line segment will be 0. Again, this was a special case of a general case. Whenever your endpoints are equal, no matter which function you integrate, you will always get 0. Example 2. You may want to pause the video now and try for yourself, because you're going to be in front of a little problem, and thinking about how you could solve it is going to be really useful for you. So what we would normally do is to find an antiderivative for the absolute value function, but then we realize we haven't been taught any. So what we could do is two things. The first one would be to try to draw to visualize what's going on, and the other one is to try to solve without drawing. So let's first draw. So that's the graph of the absolute value function. We want to know what happens between -1 and 5. And we know that this integral symbol means we're trying to find the signed area between the curve and the x-axis. In that case, the fact that it's signed will not make any difference because it's above the x-axis, so it will be counted positively. So basically, we're trying to find the sum of these two areas. Let me call them area number 1 and area number 2. So our integral is the sum of these two areas. Well, we can use our year 7 skill to find that. It's just the area of right-angled triangle. So this distance is 5. This distance is 1. And if we want the y-coordinate of this point to be able to find this distance, we can just sub in the x-coordinate into the equation of the line, and we get that this distance is 5. Same thing here, so this distance is 1. The area of the first triangle is base times height on 2, and the area of the second triangle is also base times height on 2. That's 26 on 2, and that's 13. Method 2 is doing this without drawing. It's probably not as efficient, but it will be a good review of the absolute value function. So of course, when we look at that integral, the problem is the absolute value. We want to get rid of it, and we know that the absolute value of a positive number is the number itself, and the absolute value of a negative number is the opposite of the number. So what we're going to do is split the domain into a subinterval where x is always negative, and a subinterval where x is always positive. Now on each of these subinterval we can rewrite the integral without the absolute value. If x is negative, the absolute value of x is negative x. Whereas if x is between 0 and 5, x is positive, therefore the absolute value of x is x. And from there we can use the fundamental theorem of calculus. We find an antiderivative for each of these two functions, we keep track of the endpoint, and then we sub in the values of the endpoint. And we're going to get 0 minus a half for the first one, plus 25 on 2 minus 0, and we recognize our 1/2 plus 25 on 2. Really, this is the area of the first triangle, and this one is the area of the second triangle. So we did it blindly without really looking at the drawing, but from the beginning we've been splitting our integral into the area of the first triangle and the area of the second one. Of course, we get the same result as with the first method. It's just longer and not as informative. Let's try another one. Would you like to try this one for yourself? So we realized that sketching the graph really helps, so let's do this. We recognize that this is the absolute value function which has been shifted 1 unit to the left. And we want to integrate between -2 and 5. The integral is the signed area under the curve, so since both areas are above the x-axis, they will both be counted positively. We don't have to worry about that. So our integral is really the sum of two areas. This distance is 1. This distance is 6. We know that the coordinates of these points are 5, f of 5. So really it's 5 and 6. So this distance is 6. Same thing here, sub in -2. When you sub in -2 you get 1. So this distance is 1. This integral is the sum of the area of the two triangles, so that's base times height on 2 plus base times height on 2, and we get 37 on 2. We could do the same thing as in the previous one and try to calculate this blindly without the drawing, and we would realize that we are forced to split the domain into subinterval where x plus 1 is always positive or always negative, so we can remove the absolute value. So we would be splitting into this interval and that one, which really corresponds to the two triangles we have here, because indeed x plus 1 is going to be positive if and only if f is greater than -1. So far I'm leaving the absolute value, and in that case that's the absolute value of a negative number. The absolute value of a negative number is the opposite of that number. Here the number is x plus 1, whereas the absolute value of a positive number is the number itself. And from there we can apply the fundamental theorem of calculus. As we can see, it works, but it's longer. I will let you finish this one. Let's look at another example. What we can do is try to find an antiderivative, but that's not the derivative of a well-known function. We then realize that there is a function inside a function. There is this 3x squared which is inside the exponential function. When it's like that, usually substitution works well, and we define a new variable which is the inside function. So what we could try here is u is equal to 3x squared. We know that after that we need to calculate du, which is going to be 6x dx. And then we try to rewrite the integral we have using only u and du. So I'm going to do something we didn't do earlier. I want to insist on the fact that these endpoints are values of x, although this information is already in the dx. If here you have dx, it means that those are values of x. If here you add dt, the endpoint would be values of t. I'm also going to change the order and rewrite the exponential first. So I'm getting times 2x dx, which I obtained by just moving this here. The reason I did this is because it starts to look a little bit like my 6x dx. What I could do now, since what I want is a 6, is multiply and divide by 3. If I multiply and divide by 3, it's still equal. And now I'm ready for the change of variable. So exponential of 3x squared is exponential of u. This is 6x dx, it's du. What's new is that now the endpoints will be values of u, and these values of u will be obtained by using the change of variable. So we know that u is 3x squared. This endpoint was x is equal to 0, so we just need to calculate what u is when x is 0. When x is 0, u is 0. So these values, so when x was 0, u is 0, it goes there. Now we need to look at this other endpoint. What happens when x is 2? So again, we sub in. And when x is 2, u is equal to 3 times 2 squared, which is 12. So the value we get there is 12. Usually we don't write u equal or x equal in the endpoint. I'm doing it because it's the first time we do this, so it may not be clear to you that the first time these were values of x and now they're values of u. The way this would usually be written is integral between 0 and 12 of 1/3 of exponential of u du, and you're expected to know that if here it says du, the values in the endpoints are values of u. Now we can just use the fundamental theorem of calculus, find an antiderivative of the exponential function, well that's easy, and then sub in the endpoints. And we get exponential of 12 minus 1 on 3. Let's do one more example. The method is exactly identical to the one in the previous exercise, so you may want to pause the video and try it by yourself. Again, we notice two things. First, we don't know by heart an antiderivative for this function. And second, there is a function inside a function. So when there is a function inside a function, what we may try is substitution. The substitution or change of variable that usually works is to choose your new variable to be the inside function. The sine function is inside the square function, so that's my inside function. Then I calculate du. The derivative of sine is cosine, d theta. That's good because I get my du right away. And then I know that in my initial integral, the variable was theta. Therefore, these were values of theta. And now I need to calculate the corresponding values of u. So when theta is pi on 6, then u will be sine pi on 6. So that's pi on 6. I know that for pi on 6 and pi on 3, one of the coordinates is 1/2 and the other one is square root of 3 on 2. So this is the one which is 1/2 and sits on the vertical axis, that's sine. So my sine is equal to 1/2. When theta is equal to pi on 3, then u is equal to sine pi on 3. And this time again I know one of the coordinates is 1/2 and the other one is square root of 3 on 2. So that's this one, and what I want is sine, so I'm going to read my result on the vertical axis. So that's square root of 3 on 2. Let's rewrite the integral using u only. So that's the integral in question B. Sine theta squared is u squared. Cosine theta d theta is du. When theta is pi on 6, that's the endpoint at the bottom, u is a half. And when theta is pi on 3, that's the one at the top, u is square root of 3 over 2. We may now use the fundamental theorem of calculus. We find an antiderivative for u squared, and u to the third on 3 will work. We then sub in the endpoint. I'm going to factorize this 1/3 at the front. So what I will get is square root of 3 over 2 cubed minus 1/2 cubed. Don't forget the brackets here. So square root of 3 to the third here is going to be square root of 3 times square root of 3 times square root of 3. And I can group two of them to create a 3 and keep the other one. So I'm going to get 3 times square root of 3. And I notice that my two fractions have the same denominator, which is equal to 2 cubed. That's 8. And I get this. Now I can multiply those two fractions. So I'm going to multiply those two together. And I get 3 square root of 3 minus 1 on 24. Thank you for watching this video on how to use the fundamental theorem of calculus.